Today, we start learning about quantum mechanics. Quantum mechanics is one of the most important and fascinating branches of modern physics. It describes how matter and energy behave at the smallest scales: atoms, electrons, photons, and other subatomic particles. Unlike classical physics, which explains the motion of everyday objects, quantum mechanics reveals a world where particles can exist in multiple states, behave like waves, and even influence one another across vast distances. Developed during the early 20th century, quantum mechanics transformed our understanding of the universe and became the foundation of many modern technologies, including computers, lasers, semiconductors, MRI scanners, and quantum computers. What is quantum mechanics? Quantum mechanics is the branch of physics that studies the behavior of particles at the atomic and subatomic level. At these incredibly small scales, the laws of classical physics no longer apply. Instead, particles follow a completely different set of rules that often seem strange or counterintuitive. For example, an electron does not orbit the nucleus like a planet orbits the sunlight, behaves both as a wave and as a particle. A particle's exact position and momentum cannot both be known perfectly. Two particles can remain connected even when separated by enormous distances. These phenomena are the foundation of quantum mechanics. Why was quantum mechanics needed? By the late 1800s, scientists discovered that classical physics could not explain several important observations. Some major problems included black-body radiation. The photoelectric effect, atomic stability, spectral lines emitted by atoms. These puzzles led scientists to develop a new theory that eventually became quantum mechanics. History of quantum mechanics. Max Planck, 1900. Max Planck proposed that energy is emitted in tiny packets called quanta. This idea introduced the concept that energy is not always continuous. Albert Einstein, 1905. Einstein explained the photoelectric effect by proposing that light consists of particles called photons. This work earned him the Nobel Prize in Physics. Niels Bohr, 1913. Bohr suggested that electrons occupy specific energy levels around the nucleus. Electrons can jump between these levels by absorbing or emitting energy. Louis de Broglie, 1924. He proposed that every particle has wave-like properties. This idea became known as wave-particle duality. Werner Heisenberg, 1927. He introduced the uncertainty principle, showing that certain pairs of physical properties cannot both be measured with perfect precision. Erwin Schrödinger, 1926. Schrödinger developed the famous wave equation that predicts how quantum systems evolve over time. Paul Dirac. Dirac combined quantum mechanics with relativity and predicted the existence of antimatter. Basic principles of quantum mechanics. 1. Quantization. Energy exists in discrete amounts called quanta. Instead of taking any value, many physical quantities exist only in specific levels. Example: an electron can only occupy certain energy levels inside an atom. 2. Wave-particle duality. Every particle behaves both as a particle and as a wave. Examples include electrons, photons, protons. Whether wave-like or particle-like behavior is observed depends on the experiment. 3. Superposition. A quantum particle can exist in multiple possible states simultaneously until it is measured. This principle is often illustrated using Schrödinger's cat thought experiment, where the cat is described as being a combination of alive and dead states until an observation is made. The thought experiment highlights the unusual implications of applying quantum rules to large objects. It is not a literal prediction about real cats. 4. Quantum entanglement. Two particles can become linked so that measurements on one are strongly correlated with measurements on the other, even when they are far apart. Entanglement does not allow faster-than-light communication, but it does reveal correlations that cannot be explained by classical physics alone. 5. Uncertainty principle. According to Heisenberg, the more precisely you know a particle's position, the less precisely you can know its momentum. This is a fundamental property of nature rather than a limitation of our measuring instruments. 6. Probability. Quantum mechanics predicts probabilities rather than exact outcomes. Scientists calculate the likelihood of different results using the wave function. The wave function. The wave function is a mathematical description of a quantum system. It contains information about all possible states of a particle. The square of the wave function gives a probability of finding the particle at a particular location. Okay, friends, that's the part 1 about quantum mechanics. Thanks for watching.